So can you can hear me properly, right?
Yes.
Okay, thanks.
So hi everyone, I'm Jitendra. I'm a postdoc at ETH. I work for Work Package 5 in XAIDA project with Eric Fisser. Today I will present a recently published work on how circulation modulates trends in heat extreme intensity over Western Europe and US Midwest. It was a collaborative effort with Sebastian Sippel and Eric Fisser.
So since
pre-industrial time, so Earth's temperature has been raised by more than 1 degree Celsius, and most of this warming has been attributed to human activities, as you can see this by black and red lines in this plot, and as a result, it has caused more frequent and intense heat extremes worldwide. However, heat extremes over certain regions responds quite differently to the global mean temperature rise and shows a very unusual trends. So for example, like US Midwest and the Western Europe. So this plot shows the trend in hottest 5 days period annually over Western Europe and US Midwest, which we term as like TX 5 day. Here you can see it. These trends are estimated during 1979 to 2021 using CPC dataset. So heat extremes over Western Europe has warmed disproportionately, and part of the region, particularly over the central Western Europe, like Germany and parts of France, heat extreme shows the warming of up to 1 degree Celsius per decade since 1979. This warming rate with a global mean temperature, it turns out that the heat extremes over Germany and the part of France warms up to 4 degrees Celsius for each degree change in global mean surface temperature. And the several studies have declared the Western Europe is a heat wave hotspot with a faster warming rate than many other parts of the world in last roughly 4 to 5 decades. And the blocking or the anticyclone or like high pressure systems found to be one of the dominating driver of the heat extremes over the Western Europe. And these anticyclonic activities in the upper atmosphere are basically associated with a reduced cloud cover, which allows more solar radiation to reach the ground. But on the other hand, heat extremes have not virtually warmed over US Midwest. In fact, the heat extremes have been cooled down a bit actually. Which is counter to what is most expected in the warming world. So in US Midwest, the cooling trend in heat extremes are more pronounced in the western part and southern part of this region, which offset the warming or like a weak warming trend in other parts of the region. And as a result, it turns out like overall it's a weak cooling trend since 1979. So this cooling trend in US Midwest is notable for several reasons. So for example, the heat extremes nearly anywhere else in the world has been warm during the same period. And in fact, the daily summer average temperature over the US Midwest has been increased moderately. And also the temperature over the warmest 5 nights shows the moderate warming trend. So considering all these factors, these trends, so the trends over these two regions are quite unusual and opposite. And we also examine like how unusual these trends are when they are compared against the spatial distribution of global graded trends. So the plot on the left shows the distribution of the graded trends across the globe, including US Midwest and the Western Europe. This distribution is shown by the bar plot in the gray color here, you can see it, and the regional distribution of the trends over US Midwest and Western Europe are shown by the blue and red color respectively, as you can see it here. And the dot over the gray box plot shows the average trend in US Midwest and the Western Europe. These trends are based on the era 5 during 1979 to 2021, and the spatial distribution of these trends across the globe is shown by this map on the right side. So the TX 5-day trends over US Midwest and Western Europe exhibit a substantial deviation when they compared with the trends in other regions globally. The trends in majority of grid cell across the US Midwest lies in the lower end of the distribution, as you can see by the blue distribution here, blue box plot. And the regional average trend over this region falls below the 25th percentile of this distribution. But the warming trend observed in the Western Europe are particularly notable in comparison to the trend in other regions worldwide. The magnitude of the warming trend over Western Europe exceed the trend observed in the most of the land across globally, and the average warming over this region surpassed the third quartile of the global graded trend distribution. And also the whole distribution of the trend is significantly higher than the global trend distribution. So overall, we observe that these trends over the US Midwest are not smallest globally. And also the trend over the Western Europe are not the strongest globally. So basically through this plot, I want to address the issue of the regional selection wise, because these trends over these two regions are not really in the opposite tail of the distribution, but they lie somewhere close to the 80th to 85th percentile of this global trend distribution. And if we look at the map on the right side here, so the observed trend over these two regions are also noteworthy, particularly over these two regions, because the trends are outside the CMIP6 multimodal range. So blue and red color indicate the trends between 1979 to 2021 in ERA 5, and the magenta dots in the map indicate the grid where ERA 5 trends are outside the 5th and 95th range of CMIP6 multimodal ensemble range. So if we look over the Western Europe, the trend in most of the grid cell are above the 95th percentile of multimodal ensemble. Similarly, the trend in US Midwest are also outside the 95th percent range of the multimodal ensemble. Basically, the ERA 5 shows the cooling trend over most of the US Midwest, which is lower than the 5th percentile of the multimodal ensemble range in several grid points across this region. And just to highlight that the Western Europe and US Midwest are not the only regions where these trends are outside the model range, but the trends over other regions such as the Amazon and the central part of Africa are also outside the model range. And particularly, we observe the quite good regional coherence in the trend, which are outside the model range. So it's not like the one grid cell is here and they are just randomly showing the trend outside, that they have like a good regional coherence. And which could be a potential research questions to explore further, like why these trends over like a 1/3, almost it's like a 1/3 of the global land are outside the model range. And just to get a better sense, we compare the trends in the regional average heat extremes in observation against CSM large ensemble and CMIP6 multimodal ensemble. So these plots shows the linear trend in heat extremes over US Midwest on the left side and over Western Europe on the right side. So the dashed line indicate the trend in the observation and reanalysis, and shadings indicate the 95th range of multimodal ensemble. And the solid line indicate the ensemble mean of CSM2, large ensemble and CMIP6 model. And orange color is for CMIP6 and green color is for CSM2. So the regional average trend in the US Midwest fall below like 5th percentile range, 5th percentile of both CSM and CMIP6 multimodal ensemble, and particularly the CSM2 ensemble mean shows the warming of like up to 3 degrees Celsius with a range of roughly 1.5 degree to 5 degrees Celsius. And the CMIP6 multimodal mean shows the warming of approximately 2 degrees Celsius with a range of like half degree to roughly half degree to like 4 degrees Celsius or so. But the observations and reanalysis shows the cooling of heat extremes by roughly 1/4 degree Celsius, and none of the ensemble member from the CSM large ensemble simulate this cooling trend. But in contrast to the US Midwest, in Western Europe, the TX5 trends fall within the CSM2 large ensemble range and CMIP6 multimodal range. But observed trends are at a very high end of the simulated trends. So the observed trend in the Western Europe basically lie above the ensemble mean of, ensemble mean of CSM large ensemble, and CMIP6 multimodal. So basically, so if we compare like these observed trends in the Western Europe, they are lie above like ensemble mean, and they are like far above the ensemble mean of CMIP6 multimodal. So the CSM2 large ensemble simulate warming roughly 1.5 degree to 3 degrees Celsius, and CMIP6 simulate between like half degree to 3.5 degrees Celsius. while observation shows the warming over 3 degrees Celsius. So this mismatch between observation and simulation is even larger when these trends are represented per degree global mean temperature over both the regions. And also I want to highlight here that the both CSM and the CMIP6 multimodal ensemble shows the substantial uncertainty in TX 5-day trends over both the regions, which is basically due to the internal variability. And the divergence of the linear trend is more pronounced in the US Midwest. Here you can see the range, and compared to the Western Europe, where range is like a bit smaller. And the uncertainty in heat extremes in US Midwest is like almost 2 times larger than what we observed in the Western Europe in the model world. So next we attempt to understand like why observed trends in the heat extreme intensity over these 2 regions are remarkably low and high, and why model doesn't capture the observed trend over these 2 regions. So we started with the dynamical adjustment approach, which is used to disentangle the contribution of circulation-induced changes to the total trend. So basically, this approach is widely used to determine the proportion of variability of any target variable, let's say TX 5 days here, that can be attributed to the atmospheric circulation change. So in this analysis, we use the principle from statistical learning, and we employ a regularized regression to establish a physical relationship between geopotential height at 500 hectopascal and TX 5 day, which is our target variable here. So basically, this relationship enables us to separate the circulation-induced contribution from the externally forced component. So here it is important to note that we detrended G500 to remove the effect of thermal expansion of the troposphere, which is primarily caused by the forced warming. So precisely, we subtracted the daily global mean G500 value from the daily G500 at each grid and at each time step across the circulation domain. So the extent of circulation domain is shown by the red box here in this plot. So this detrending process removed the influence of thermal expansion of the troposphere due to global warming. However, it does not imply that the circulation changes are solely due to the internal variability, as external forcing can also affect the circulation, circulation, and subsequently can modulate the characteristics of the heat extremes. So here is the detail of the data set we used and the model setup. So we consider the detrended G500 as a proxy of the circulation. And we trained the model on pi control simulations of 2070 years. And here we trained the ridge regression model on the pi control to avoid any false learning of the model due to forced warming. And the predictive value from this regression model, which has been shown in the equation in the previous slide, defined as a circulation component. And the residual term from this regression is defined as the thermodynamic component. And the residuals are basically expected to contain the externally forced component, but it can also contain effect from local feedback such as soil moisture, atmosphere interaction, and so on. Yeah. So this plot basically shows the contribution of circulation-induced trend to the total trend over Western Europe and US Midwest during 1979 to 2021. So the box plots on the right shows the circulation trend in CSM and CMIP6 multimodal ensemble over the US Midwest, and the blue and these purple symbols represent the observations and reanalysis. And similarly, the box plot on the left side indicate the circulation trend over Western Europe. So if we look at the if you look at the US Midwest, and the observation shows that circulation changes induce substantial cooling trend. So it's roughly like 0.2 degrees Celsius per decade, and which is roughly a cooling of 1 degree Celsius since 1979 or so. And we also note that the cooling trend are consistent in the observations and the reanalysis. So both observation and reanalysis shows the consistent cooling trend due to the circulation. But model seems to be really off in simulating the observed circulation cooling over the US Midwest. So the observed cooling trend in US Midwest are substantially lower than the first quartile of the trend distribution from CSM large ensemble and SIMIP6 multimodal ensemble. In fact, CSM large ensemble mean indicate the positive trend, and only one ensemble member capture the observed trend. However, none of the ensemble member reach to such cooling trend when these trends are expressed per degree Celsius of the global warming. However, in case of SIMIP6 multimodal ensemble, the circulation trend in observation lie at basically the lower edge of the model range, and only few individual member from SIMIP6 multimodal ensemble shows such cooling trend. And overall, SIMIP6 simulates lower circulation compared to the CSM to large ensemble, which leads to relatively smaller deviation from the observed trends. However, more effort is needed to understand whether these like couple of members from the SIMIP6 reproduce this cooling trend for maybe correct underlying mechanism. But in contrast to US Midwest, over Western Europe, the circulation induced changes contribute to an additional warming of roughly 0.2 degrees Celsius per decade. And interestingly, the circulation-induced warming account for like 1/3 of the total observed trend. So in case of the model, both CSM2 and the SIMIP6 shows the identical distribution, the distribution like more or less same, with a positive but weak contribution from the circulation. And the observed circulation trend in the Western Europe closely align with the third quartile of both CSM2 and the SIMIP6 multimodal ensemble, but they considerably exceed the third quartile when if we adjust this trend with relative to per degree global warming.
Yeah, and in case
of the force thermodynamic trend, so this map shows the force thermodynamic trend. So force warming is much weaker over the US Midwest, and which can be potentially due to land use changes and the irrigation. And the circulation-driven cooling trends are strong enough. So here you can see they are like almost 1 degree Celsius, like in the last 4 to 5 decades or so, and strong enough, and they reverse the weak thermodynamic warming. And like if we combine these, and this overall results in a weak cooling trend over US Midwest. And similar to the circulation, observe the thermodynamic trends over the US Midwest, like a fall below the entire distribution range from the CSM2, and it's simulated by only few members from the SIMIP6 multimodal ensemble. And while in the Western Europe, the TX5D trends are basically dominated by the thermodynamic warming. So to be precise, the thermodynamic change cause warming almost 0.5 degree Celsius per decade, which is roughly a 3 degree Celsius rise for each degree change in the global mean surface temperature during that time period. And it accounts almost for like 2/3 of the total warming. And when it combined with the amplified warming from the circulation, and then it results in an overall warming of roughly 0.8 degrees Celsius per decades or so. And similar to circulation trends, the observed thermodynamic trends are also are still within the ensemble range, but they lie at the upper end of the distribution from SIMIP6 multimodal ensemble, and it's somewhere like in between and a little bit higher when we compare with CSM to large ensemble. So the both circulation thermodynamic induced trends are at a very high end of the model range, and which explain why together the total observed trends over Western Europe are at the high end of the model range. So we also estimated the trend in the temperature over hottest 5 nights over Western Europe, and which we define as the TN5 day. And this plot shows the observed and simulated trend in the TN5 day during the same period. Basically, it's 1979 to 2021. And the vertical dashed line represents the trend in the ERA 5, and the histogram shows the range of TN5 day trends in SIMIP6 and CSM2. So over Western Europe, we noticed that like observed trend in TN5 day are bit smaller than the TX5 day trend, and TX5 day trends are roughly 0.8 degree to like a 1 degree Celsius per decade, but in the trend in TN5 day it's roughly like 0.4 degrees Celsius or so.
But the one
Interesting thing is that the TN 5-day trends are well within the both CSM2, large ensemble, and CMIP6, which is not the case for the TX 5-day. So the stronger increase in the daytime temperature and the relatively weak increase in the nighttime temperature indicate the increase in the diurnal temperature range, which could be due to the reduction in aerosols and the cloud cover. And because aerosol tends to have offsetting effect on the daytime because the aerosols basically have a offsetting effect on the daytime temperature more. So here I want to highlight that it's not necessary that this hottest 5 days and the hottest 5 nights temperature occur simultaneously, but we have checked it here and find that in most of the cases they occur together. Interestingly, we noticed that the observed thermodynamic trends in TN 5-day are at the lower end of the model, and model shows like a little bit more warming due to the thermodynamic in the TN 5-day. Which is like obviously quite interesting and also contrary to the TX 5-day thermodynamic trend, which are basically at the high end of the model range somewhere here. So this suggests that the model missed the thermodynamic warming in the daytime temperature, which can be potentially due to the reduction in the aerosols. Yes, so recently we published another collaborative effort, which was basically led by Dominic Schumacher. So in this paper, he shows that the underestimation of heat extreme trend in Western Europe is even much more pronounced in the regional climate models from the Cordex. So what he did here, so he considered the ERA 5 and set of CMIP6 and RCM's regional climate model, which shows like a background warming somewhere close to the ERA 5. And he clearly showed that the warming in ERA 5 is at a very upper end of the set of CMIP6 model, and none of the RCM reaches to that level. Basically, RCM completely missed that observed warming by a large margin. So he also pointed out that the Cordex model with a constant aerosols shows the weak surface net radiation trend, and the Cordex simulation with the time evolving aerosols, on the other hand, basically, they show like a net radiation increases broadly, which is consistent with the ERA 5. So you can check out this paper for more details. So it was a short presentation. So coming to the summary and few takeaways. So here we investigate the trends for 2 regions, which shows very unusual behavior. So we here shows the circulation play a crucial role and amplify the trend in heat extreme intensity over Western Europe and dampen over or even reverse the trend over the US Midwest. So over the US Midwest, the circulation dampened the trend in the intensity of hottest 5-day period by roughly 0.2 degrees Celsius per decades or so, which is like approximately 1 degree Celsius since 1979 or so. But in case of Western Europe, the circulation changes induce a warming trend in heat extremes of like similar amount, like 0.2 degrees Celsius per decades or so, and which account for at least 1/3 of the observed trend. So the observed circulation and thermodynamic induced warming is at the high end of the model range over Western Europe. And the combination of these two facts basically contribute to the fact that the total observed trend is at the high end of the model range over Western Europe. So basically our results imply that if the circulation-induced trends are externally forced, then Western Europe may continue experience a rise in the intensity of heat extreme as they can further intensify in the warmer world. But on the other hand, these cooling trends may continue dampening the warming trend over the US Midwest, which maybe provide like a more favorable conditions for the agricultural activities and so. But if these trends are a result of like unforced internal variability, which is basically inherent in the climate system, then they likely reverse in the upcoming decades and can lead to a bit slowdown of the rise in heat extremes over Western Europe, and may lead to the warmer condition over US Midwest. Thanks. That's all I have today, and you can find the more detail here in this paper, and I'm happy to discuss if you have any question or feedback.
Thanks.
Thank you very much for your presentation. So now, if anyone has questions, please unmute yourself or view the chat. For example, we have several questions on the chat.
Mhm. Should I read out?
These questions in the chat, or
Yes,
Mhm.
or Ted, if you want to ask, as you have your raised hand.
Sure.
Yeah,
I'll
so I
ask.
first question is from Ted.
Yeah,
Ted, you want to? Yeah.
Yeah, just so normally I'm used to the dynamical adjustment. You think of Clara Des's papers, the residual is very, very clear. It's like it doesn't have any spread. That's for a single model, of course. And you really, isolate the thermodynamic part, which is, doesn't have the same level of variability. But you seem to have quite a lot of variability in your residuals. Of course, for the CMIP, it could be different model responses, but for CESM, it should be internal variability only. So I guess that I don't know how do you interpret that? It means that you're not capturing a lot of the variability from your dynamical adjustment, it seems to me.
yes, I think it's a
Basically, due to like how we set up this regression model, and that's the only thing I can say, because of like model is not able to capture like full of the variability, I guess. And yeah.
But it weakens a lot of the conclusions, I think, because if you isolate the circulation component, and what you have left looks like a very clear forced response, then well, the interpretation is reasonably straightforward. But maybe the second question is not unrelated to that, because you have basically a negligible there it is. Yeah, the Middle East, Midwest US has a tiny thermodynamic trend. I mean, is that really plausible? You mentioned soil moisture, but I mean, what was that just a guess, or do you have some evidence that there have been changes over 50 years that in the real world that could possibly do that? Because it's very hard to interpret the results, it seems to me, if there seems to be a lot of circulation variability left over, which appears to be the case.
yeah. So basically,
In terms of like this weak thermodynamic trends, there is a literature and they suggest like a land use, land change activities, particularly that irrigation might have an influence on the daytime temperature. But if we consider like why I'm saying it, maybe because of some local factor, because when we see the trend in like those same 5 days during the nighttime temperature, and we see like a little bit warming trend, and I can show you that plot, probably I should have.
yeah. So if you look at this,
So basically these are the trend in the hottest nighttime temperature and over US Midwest, and we see a little bit of warming. But if we look at the trend in the daytime temperature, and they are showing a little bit cooling, so that's why I anticipate it might be due to some like maybe because of some local factors like irrigation. Another thing, they are having high like this dampening effect on the like, really peak temperatures, and due to maybe like more latent
cooling,
or because of like more evapotranspiration because of the irrigation.
Okay, that seems like maybe a more important result if it's true. I mean,
yeah.
With the Midwest, there were always issues if the trends are very long term because of the Dust Bowl, but this is much more recent.
And in fact, like
there is not a very strong evidence. Yes, I cannot say it's because solely due to the irrigation, and there is a literature they say it's because of the internal variability and from like some like large scale boats, like for example, like Atlantic and Pacific Ocean, these SSTs, they might also drive this like a wormhole over this whole eastern US. So it's kind of a bit hard to say what's driving these weak thermodynamic trends over US Midwest. Yeah.
Yeah, Scott, please.
Thank you for a very interesting and thought-provoking talk. I really enjoyed it. It's really quite relevant to XAIDA. One thing I couldn't quite appreciate, and forgive me if you actually explained this early in your talk, but I was just trying to understand your diagnosis of the thermodynamic and the circulation trends. Do I understand correctly that your thermodynamic trend is just a residual of your total trend minus the circulation trend? I'm just trying to, yep. I'm just wondering, you've defined these on regional, well, on 2 regions, but I'm just wondering, can one define this, on as a function of space in terms of a spatially varying quantity? Because I'm trying to understand whether these 2 indices are a faithful representation of the things that we think they are. So we're saying that, okay, we've got a circulation defined temperature trend, and we're saying what is not that is defined as a thermodynamic one. I'm just trying to understand whether we can actually confidently say that, and one can do that, I suppose, by just looking at a spatially defined index. And again, if you've already done that, I apologize, but just to add confidence to these things that we're attributing to these 2 factors.
Actually, I didn't get your a question specifically. Yeah.
Okay. The question was, you've defined these 2 components of trend, thermodynamic and circulation, on 2 regions. What do they look like on a spatially defined domain? As in, if you don't aggregate them into regions, what do they look like across the hemisphere or across Europe and the US?
Yeah,
I can. So I think I should have this spatial map as well.
That will have a lot of information for us to identify what we actually mean by thermodynamic and the origins of these trends.
I don't have this map ready for the thermodynamic trends, but for the circulation trends, so the circulation-induced cooling is more pronounced in the southern part of the US Midwest and eastern side. But these positive trends from the circulation is mostly concentrated over the Germany, France, and that region, and which is like a mix or a very weak over the Spain. And so we consider this whole domain. So it's if we average out, it turns out roughly 0.2 degrees Celsius, but it's more pronounced over the central part of the Western Europe, actually. And in terms of, I think I should have the spatial map of thermodynamic trends in my paper. So I think I have to pull out that figure. But this is the spatial pattern of the circulation-induced trends over these 2 regions. Yeah.
Okay. So especially the circulation trend, this is over summer. So the summertime NAO, does the spatial characteristics of that look similar to what you're seeing over Europe, the spatial distribution and circulation trends? Because it looks quite like a dipole, doesn't it? Just trying to understand the.
So you mean dipole over
the Europe, or if the dipole?
Yes.
Yeah. Mm-hmm.
So I'm just trying to identify the origin of the circulation trend in terms of a trend projecting onto a natural variability, or something else like soil moisture or something like that. Or that could be thermodynamic, perhaps. Yeah.
Yeah, just want to
give you some glimpses. So we are just trying to separate these trends, out of this total circulation trend, how much is the forced and how much is just due to the internal variability. And we are doing some model experiment, and it turns out of this circulation trend over this region, and it's purely due to the internal variability over Western Europe. But there is quite a bit forced response in the circulation trend over US Midwest, and forced response is also leading towards cooling trend. Yeah.
Yeah. Okay. Very interesting work. Thank you very much.
There's been a little bit of follow-up on Ted's questions on the chat. If you want to check or you want to comment on something while we wait for more questions.
So could I go to the next question? I think
it's in the chat. I said Sonia.
yeah. So is there literature showing
A clear forcing element from the irrigation? So I'm not sure. Like basically, there is a mixed response and like there is a mixed evidence. So there is a couple of literatures that says like there is a quite a lot influence from the irrigation, which is dampening these
the temperature extremes?
extremes basically, and which is leading to like overall cooling. But there is some literature which says like it might be due to the internal variability or some influence from the different sea surface temperatures, maybe in Atlantic and the Pacific. So it's not only the US Midwest, like mostly whole like Eastern Europe, it's in summer, it's so it's like a bit of the cooling and heat extremes.
Yeah, maybe if I can add. So I guess my comment was more in the US that indeed there is a literature suggesting that there's been a forcing impact from irrigation. So that would be an additional forcing. Maybe since I have the floor, I could also comment on what has been discussed on the variability that is remaining. And to me, it seems consistent with results we had with Catherine Verley, in which we looked at basically the contribution of soil moisture versus circulation and SST actually to the extremeness of hot extremes. And basically circulation only explained about half of it. So the other half was from soil moisture. So of course we have variability, which is coming from persistence. So for instance, if you have a dry spring, you will have some impacts and on the temperature in summer. So you have this type of variability that is introduced. And to me, this seems consistent with your results. So. But that's definitely very interesting. Thanks for the presentation.
Maybe just, but you don't mean the circulation isn't important. It's just that the synchronous circulation it doesn't explain everything. You have to look at the precursors and the whole seasonal, because the SSTs are coupled to the soil by precipitation, by circulation, right? So I mean, I don't think we should think of it as soil moisture or circulation. It's a question of what are the factors because they're coupled, right? It's just a question of what factors at what time, conditional independence kind of, right?
If I can jump in, I guess that maybe not more of a discussion with Ted, but maybe Jitendra, you have an opinion on this. I mean, about the role of soil moisture versus circulation, certainly a lot of the anomaly of soil moisture in summer will be the result of circulation anomalies you have, for instance, had in the spring. Nonetheless, there is also a thermodynamic component in the context of climate change that we know we have a mean drying, for instance, in Central Europe. So you cannot limit this to just the circulation aspect, because you have also a force signal.
But you would hope that would be more systematic. And I guess there's also difference across models rather than within model. These are different questions too, because different models will have different parameterizations, but the real world has only, or a single model has only one. They don't have differences in the physics,
Just a very brief comment. Maybe I agree with the discussion before with kind of soil moisture and circulation are important. I just pasted an old paper from Anna Merrifield in the chat, who actually showed that if you apply dynamical adjustment on summer, then what you get as a residual is actually a lot soil moisture, but also the thermodynamic of force response. So I think it is consistent, but the model, of course, doesn't explain everything. It just takes the synchronous circulation. So of course, there's the coupling with soil moisture and SSTs.
Okay, I think we covered all the questions on the chat. If anyone else has a question, please raise your hand or mute yourself. If not, we can wrap up the discussion. Okay, so thank you very much to the speaker for the presentation and all of you for attending. So we can finish this 5th session of the XAIDA webinar here, and we hope to see you in the next seminar, which will take place the 21st of May. See you soon.